We have booster ignition and liftoff of Columbia, reaching new heights for women X-ray astronomy.
The main thing that Chandra does is take these superb sharp images.
Nothing as beautiful as Chandra sailing off on its way to work.
Supernovas are the remnants of catastrophic explosions, and they are among the favorite targets of scientists who use Chandra. For good reason, too. Supernovas and their remnants have proven to be extremely important in understanding topics ranging from the birth of our solar system to the history and composition of the universe itself. They can help astronomers understand the origin of the elements that are necessary for life. They can be used as cosmic laboratories for studying extreme physics, and they also serve as distant lighthouses that tell us about the accelerating expansion of the universe. Dr. Patrick Slane of the Chandra X-ray Center explains why he's interested in studying supernovas.
When I took my first astronomy class in college, the thing that fascinated me the most was how massive stars evolve. They're the ultimate picture of life in the fast lane. They burn bright, use up all their resources in a stellar blink of an eye, and end their lives in a massive collapse. But they do go out with a bang. They leave their mark too. They take simple hydrogen and helium, turn them into heavier, more complex elements, and distribute them out into space, where new stellar systems enriched with these elements can form. The oxygen we breathe, the calcium in our bones, the iron in our blood, were all provided in the demise of earlier massive stars. Who can resist a story like that?
But how are supernovas created? Pat Slane explains what happens before the supernova during the typical lifetime of a star.
All stars are actually destined for collapse. Stars form when gravity pulls large masses of gas together. The gravity pulls the gas inward toward the center and heats it up. This makes the gas radiate, which means it loses energy. If you can put energy into the gas, you could push it apart, fighting the gravity. But when energy is lost due to radiation, the opposite happens. It collapses even more. It's a vicious cycle that would cause the gas to compress itself indefinitely if it weren't for the fact that eventually the temperature becomes high enough to ignite nuclear fusion. This produces a high pressure inside the star that can hold off the gravitational collapse, at least temporarily.
Let's hear what happens when that star's life comes to a close.
When hydrogen runs out, this ignites a new fusion process, converting the helium into heavier elements. If the star is about 8 or more times as massive as the Sun, this process of fusion, fuel depletion, collapse, new fusion continues itself until the core is composed of vaporized iron at a temperature of several billions of degrees. But the process of iron fusion doesn't produce energy, it uses it. That means that from this point on, there's nothing to stop the crushing weight of the star. In less than a second, the entire core collapses, compressing the very center and triggering a massive explosion in which all but the very core of the star is blown out into space. These explosions, supernova explosions, are the most violent events in the universe.
But a star's story does not end with its fatal collapse. Instead, a star's death can be a transformation as its stellar ashes are recycled into the space around it. For more information about the Chandra X-ray Observatory, visit our website at chandra.harvard.edu.
This was a production of the Chandra X-ray Center, Cambridge, Massachusetts. NASA's Marshall Space Flight Center manages the Chandra program. The Smithsonian Astrophysical Observatory controls science and flight operations from the Chandra X-ray Center.